So yes, thank you for the introduction. So I'm going to be talking about basically the challenges of performing testing for HCl, both from the point of view of a test house performing the standard reference method testing, and a little bit on the challenges that the CEM system sees as well. My first slide, actually, Dave's given me a very nice introduction already, but my first slide, if I can get it to show the next slide, was a little bit about my background, but really just to highlight that I do still work out on site. A lot of the information in this presentation is either taken from personal experience or from the experience of projects that I've worked on in the past. Predominantly over the last few years, looking at 14181 projects, calibration of CEM systems for HCl. And as it says on there, I'm still an MCERTS team leader, so I still have the joy of heading out on site and seeing this work being done in the field as well. So some of the actual sort of real life practicalities of what the guys need to do on site in order to get a reliable result, the best result that we can get for HCl measurement. So really, too many slides, there we go. Where this all came about, since the publication of 14181 back in 2004, we've been required to validate CEM systems on site against the measurements that the test house might come in and perform. So really, since 2004, when that comparison measurement has been done, we've been noticing issues getting CEM systems and SRM measurements to agree. Obviously, it's not specific to HCl, but HCl does seem to be a particular problem. So it has proven challenging, but over the years, a number of issues have been highlighted, a number of best practices have been highlighted, and really it's going through some of these examples that I wanted to do today, just to look at what can be done to improve the result and get the best possible calibration of the CEM system. So the main topics I wanted to talk about are the pacification of sample systems, some differences between the way that dry and wet gas appears to be handled by the sample system, some specific issues around gas regulators, use of high temperature lines and possible cold spots within those lines, or more likely the junctions between lines and the analyzers, ambient temperature effects, a big one on ammonium chloride, which does seem to be a particular issue. And a look at validation systems for the test house equipment when it's used on site. So I'm just going to work my way through those and try and give an explanation of where we see issues and what maybe can be done about it. So to begin with, looking at the difference between a dry gas and a wet gas. So when a test house comes to site, installs their sample system, we have to perform a number of validations. So we're working to whichever relevant European standard, which I'll come on to in a little while. And we have to perform a validation of the system. Those validations at the moment, predominantly in the UK, are done using a bottle of dry gas. So we go and acquire a cylinder of HCl and inject that into the analyzer, or potentially straight down the sample system through the sample line, the filter and the probe. And into the analyzer. And the problem with dry gas is it does seem to stick to various components on its way down, which means that you need to pacify the sample system. You need to make sure that if there are any active sites in the sample system where HCl could react or stick, that those are pacified over a period of time before you get a valid result. And the problem is that at the moment, using a dry cylinder, this can easily take anywhere from 20 minutes to 2 hours. And as you'll see in some of the slides in a little while, that 2 hours could actually be vastly longer than that as well. One of the things that I personally have done in the past is to use wet calibration systems, so a vaporized HCl solution, and certainly the response times on that have seemed to be much faster. Lab response times on a wet HCl solution can be down in the minutes, sort of 3, 4, 5 minutes, rather than up in the sort of 1 to 2 hours period that we've seen on dry gases. So dry gas pacification of systems is a particular issue. One of the things that is of concern is that the pacification time can be affected by other issues, which can also then affect the sampling. So the sampling performed by the test house, but also the sampling that the CEM analyzer is doing, can be affected by a number of different issues. And all of those will also affect the time it takes to get a stable result from a validation of a system. So the first one is the sample system temperatures. So everything should be heated up to 180 degrees for monitoring HCl. But anywhere where there is a junction, so the obvious one is the junction between the heated sample line and the analyzer. If that joint is not lagged and kept warm, then you see a cold spot at that point. And what we have noticed is that if any joint is left unlagged or unheated, it does slow down this pacification time quite substantially. So we get faster, stable results if everything is kept hot. Some of the materials used as well. So generally heated sample lines are PTFE. Fittings tend to be stainless steel, but there could potentially be other materials in there as well. One thing in particular is the material used for the filter. So if you've got a filter in the sample probe, it could be PEEK, it could be PTFE, it could be a sintered metal. There's lots of different filters available, but the type of material you use and even the size of the filter can have an effect on how long it takes to get a stable result when testing a system for HCl. Sample system contamination is a big one. If you could imagine that you've got a site that's using perhaps lime injection to control HCl emissions, if that lime were to build up on the sample system, possibly in the line, perhaps on the particulate filter that's used, you've essentially got yourself that little scrubber. You've got a coating of lime on the filter. Your HCl gas in the stack is passed through that filter, which scrubs some of the HCl out. So the analyzer itself may be getting an accurate result, but the sample system is removing potentially some of the HCl. And oddly enough, stack concentrations of HCl can be an issue. Now, this one's more of an effect on a CEM system, and it tends to be on a test house coming in and doing a 1 or 2 day test. If the stack has particularly low concentrations of HCl, then when a validation check is done, the sample line that it's injected down hasn't already been pacified for HCl because there was no HCl in the stack, and it can take a long time to get a stable response. If you've got higher concentrations of HCl in the stack, then it will have already pacified the analyzer whilst it's on sample. And one of the things that test houses have been doing over the years is to put our analyzers on sample before we need them. So perhaps put them on the night before the testing is actually going to take place, leave them running on the stack on sample overnight so that the HCl in the stack can pacify the sample system so that the validation checks then are more reliable and faster. But obviously that relies on there being a reasonable concentration of HCl within the stack. So there's a few things there that can affect the pacification of a system and how quickly you can get a reliable response from an analyzer. And obviously this is related to the sample system more than the analyzer itself. So it's taking particular care with the configuration of the sample system, which can affect the response time. Now, this next slide, although we think there was probably something going on here, it's a very nice example of how long a pacification can be. So the blue line that you can see on the graph here is a CEM system, which has been monitoring on that stack for many years. So any pacification that needs to take place on the sample system for the continuous monitor is already been done. And you can see there that it's tracing HCl concentrations anywhere between sort of 20 and 30 over time. Once the stack once the test house comes on site, installs their system into the stack, you can see the red line is the results from the portable system. Now that system hasn't been pacified for HCl before this test has started. And you can see it's taken, I would say, around 14 hours from the moment the sampling was started before the mobile analyzer, the unpacified system, started to agree with the CEM system. So we can see there that there does seem to be a very long pacification time. Now that 14 hours is unusual. Wouldn't normally expect to see it take that long. And we think in this case, there probably was quite a substantial cold spot or a heated line failure or something of that kind. But it is a nice example of just how long it can take to pacify a sample system if care isn't taken to the configuration of that system. The next thing I want to talk about, again, probably more related to the test house operation rather than the CEM system. However, if a site operator was carrying out regular qual-3 drift assessments of their system using dry gases, then this may well apply to them as well. So what we have noticed over the years is that HCl regulators used to get the gas from the cylinder can have quite an effect on how long it takes to get a stable result when doing an analyzer check. Obviously, everything in that cylinder that comes into contact with HCl needs to be resistant to corrosion from the HCl. But even on the stainless steel regulators that we use, what we've noticed is over time, although I don't think it is rust, there is a brown rusty appearance that appears inside the regulators. And the older the regulators get, the more that buildup becomes evident and the longer it takes to get a reasonably fast response from the analyzer. This is particular in relation to dry gases because of the effect of it being a dry gas. So what we've seen is that sticking a brand new regulator on there, you get a much faster response time. But obviously regulators aren't cheap. We're not going to buy a new one every time we do a system. But there may be a need to be looking at replacing regulators more regularly than you would for any other gas. What we've also noticed is that just simply swapping the stem that connects to the cylinder to the regulator body can have quite an effect on speeding up pacification times as well. So there's one there to be looked at for improving the speed of a pacification when trying to do an analyzer validation, just using good quality regulators, possibly purging those regulators out. There's one there to be looked at for improving the speed of pacification when trying to do an analyzer validation, just using good quality regulators. The other thing to consider is the length of the sample lines that are used. Obviously, the longer the sample line, the more material there is there to be pacified. So keeping heated sample lines as short as possible will improve the time that it takes to get a stable response through to the analyzer, but also worth considering any other lines that are in use as well. So if you're using cold lines to run your gases from your cylinder to where your test point is, the shorter those lines are, the less HCl loss there will be along the way. The more reliable the result is and the faster the pacification of the system should be. In terms of cold spots in the sampling system, unfortunately, there's not been an awful lot of measurement done. I was once able to do a little bit of testing on this. We spent half a day just looking at the effect of cold spots. What we tried to do was by having a 5-inch section of unheated stainless steel between the analyzer and the heated line, so that section of the sample line was able to reduce in temperature. So it was unheated, it wasn't lagged, it was just left at ambient. And we measured the temperature of the inside of that stainless steel tube while sampling was undertaken. So the heated line was 180 degrees. Just that 5-inch unheated section of stainless steel dropped the sample down to 130 degrees. And in doing so, we saw a reduction in the HCl value of around about 50%. Now, unfortunately, I think we did this test the wrong way around. We did the test with a cold spot in there first. So we don't know whether or not that loss of HCl of 50% was due to just a long pacification time, or whether it was definitely down to a drop in temperature. But it does suggest that cold spots can have quite a dramatic effect on how the sample system transports HCl into the analyzer. And then some fairly anecdotal evidence to do with ambient temperatures. Now, this appears to be more to do with getting the gases from the cylinder. So we've already said that we know that HCl can essentially stick to surfaces. It seems to slow as it passes through stainless steel and as it passes through the PTFE, but it also seems to stick inside the cylinder. And that effect seems to be worse when the cylinders are cold. So if your cylinder is kept nice and warm, we seem to get a faster pacification. If it's particularly cold, it does seem to slow the pacification down. And on one particular case, we did actually try sitting a cylinder of HCl in a pile of snow. So the cylinder was at 0 degrees. And we never actually got a stable result. It was continually climbing, never reached its stable concentration, never reached the cylinder concentration before an entire cylinder had been passed through the analyzer. So although it's one instance and it's fairly anecdotal, it does suggest that maybe ambient temperatures and cylinders is a concern as well. The big effect that I really wanted to talk about today is with the use of SCRs on site. So this is where urea or ammonia is injected into the gas stream to reduce NOx emissions. And this does seem to be causing us particular complications when it comes to getting an agreement between a test house result and a CEM system, or essentially any two differing systems on site. So taken directly from Wikipedia, not the most reliable source, I realise, but there we go. Ammonium chloride. So ammonium chloride is formed when there is both ammonia and HCl present. So by reacting the two together, you can form ammonium chloride, which is a solid white crystalline salt. The other problem we have is that if you have ammonium chloride salts present and you heat those up, they can sublime or possibly decompose back into ammonia and hydrogen chloride gas. So not only have we got the complication of the HCl and ammonia that we're trying to measure disappearing because it becomes a salt, we've also got the issue that if the salts are present and they are heated, we then get ammonia and HCl, which isn't coming from the process, it's coming from the decomposition of the salts within the sample system or potentially within the stack. So the issue really is that the ammonium chloride salts won't pass through the filter that the analyzer uses. So depending on where that filter is, depending on the temperature that that filter is at, we may or may not be able to detect that on the analyzer. So if the filter is stopping ammonium chloride salts, then you'll be losing the HCl and ammonia that you're trying to measure. And there is some discussion to be had really as to whether or not the emission at that point is particulate because it's an ammonium chloride solid, or whether the emission is HCl and ammonia. And it really depends on what condition they were in the stack at the time. And stack temperatures and indeed sample system temperatures seem to have quite an effect on whether you get the two gases, HCl and ammonia, or whether you get solid salts. So again, there's not a huge amount of validation work that's been done on this, but over the years we have managed to collate some data together. Unfortunately, because of all the other issues that I've already mentioned in relation to sampling of HCl, it's difficult to tell whether the effects that we see in these next couple of slides are to do with pacification issues, process issues, or whether this really is stack temperature and ammonium chloride salts. So the trend that you're looking at here, you can see a shift in stack temperature, which occurred at the same time as an HCl shift. Now, it's possible that whatever caused the shift in stack temperature, which has gone from around 145 degrees down to about 132 at its lowest point there. And whatever caused that shift in the process stack temperature may have also caused a drop in HCl emissions. But it's possible that at 145 degrees, the stack temperature was maintaining the gases as gases. So we were seeing HCl and ammonia on the analyzer at reduced temperatures. We were seeing the formation of salts, which were being stopped by the filter. And we're then not seeing the HCl and ammonia coming through to the analyzer with a drop in the HCl results there down to sort of 2 or 3 milligrams. And then as the stack temperature has gone back up quite quickly over a period of time, if those salts have been formed, we're then heating those salts back up in the stack and releasing the HCl and ammonia. And in this case, you can see the HCl slowly starting to climb back up to its previous level again. Another example there, we only carried out spot checks for temperature on this one, but this is a comparison between a CEM system and a standard reference method, a test house system coming in. So two separate independent systems looking at HCl. One a little noisier than the other, but generally they are agreeing to begin with. You can see that the CEM system has only got a maximum range of about 8 milligrams on here, so it's capping when the HCl goes above that, whereas the test house data is seeing much higher results at that period of time. But it's the step changes that were of interest because those step changes occurred as the stack was changed in temperature. Now, again, it's hard to say whether that was process related, but there is some suggestion there that changes in stack temperature is either breaking down and decomposing the ammonium salts into HCl and ammonia, or possibly that those are being formed into salts at lower temperatures and not being formed into salts at higher temperatures. So really the effect is to look at the sample system at the stack temperature and see what can be done. Now, what we're trying to do here is make sure that if a CEM system is measuring your emissions and it sees those emissions as HCl or ammonia, that when the test house come in and perform their measurement to calibrate that CEM system, that we get the same result. So we need to make sure that the two systems are as similar as they can be. Now, what I have done is we've done trials where a CEM system has been given a fairly stable reading, say 8 or 9 milligrams for HCl, and we've turned up with 3 different sample systems. We've used an unheated in-stack probe, we've used a heated in-stack probe, and we've used a heated in-stack probe with a heated filter on it. And those 3 different sample configurations gave dramatically different HCl results. Now, this was done on a stack that we know to have ammonia in the stack. We were getting a high result for ammonia on both the CEM and test house data. So we did expect there to be a fairly large amount of ammonium chloride visible in the stack. And we could see this effect. So just matching sample systems, looking at the stack temperatures and looking to see whether this ammonium chloride salts is an issue can be a key thing to getting agreement between the test house data and a SEM system data. Okay, talking again about the test house in particular. Test house, when they come to site, if they're using an FTIR to measure HCl, as we often do, quite often we will try and use a similar method to what the SEM system is using. It does seem to give the best comparison, the best quality calibration functions, the closest agreement. So we generally would bring an FTIR to site. Currently, if we're using an FTIR since 2019, we'll be following European method 17337. And that method says that the analyzer sample system in particular has to be validated against the most reactive of the species that you're looking for, which obviously if HCl is a target species, that is going to be the most reactive. The standard says that test gases can either be derived from a cylinder. It does allow for the use of wet vapor generation systems, but it also allows for the use of analyte spiking. So just looking at the analyte spiking as an option, this originally came from the American method, the ASTM method, where we were using gases injected from a cylinder up to the sample probe so that they were transported through the sample system from the probe down into the analyzer as a mixture of both the HCl test gas and the stack gases. The idea being that the moisture in the stack gas will stop this pacification effect. If there's moisture present in the sample system, it tends not to stick to all the components on the way down, and we should get a faster result. Now, the American ASTM method uses a relatively low concentration at relatively low dilution rate, so there's quite a high percentage of stack gases. So any change in the stack gas concentration of HCl can have a huge effect on whether or not this analyte spiking method works to validate the system. Under the European standard 17337, that dilution ratio, the ratio of HCl injected to the stack gas, was increased. So we can use anything up to a ratio of 9 to 10. So we've got far more test gas being injected, but we're using the moisture content of the stack to try and transport that HCl gas into the analyzer. Also, the concentrations that are used as the test gas are increased in that procedure as well, up to anything up to 3 times the ELV. So up at those concentrations, we did some testing to see whether or not we managed to get an increase or perhaps a decrease in the response time. Faster result, more stable result from the system. And we've done quite a bit of testing on this over the years. A large project last year to see whether or not analyte spiking was a really viable method for validating the systems. And what we've seen is, yes, there is a slight increase, but not dramatic, not really enough to warrant the additional hassle of trying to do an analyte spike on site. And we think this is probably caused by some of the effects that I've already spoken about, the cylinder regulators being old, long lengths of cold tubing where you've got tubing coming from the regulator. And to make that worse, we then have additional equipment in there. So in order to feed your test gas up to your sample system, we're using flow controllers to monitor or to control the flow of HCl to get the dilution ratio that we need. But that's adding additional equipment into the cold side of this, which could cause further areas, further materials where pacification effects can occur, and it slows everything down. So although the analyte spike does seem to improve the response for the gas being carried from the probe tip to the analyzer, you still have the issues of getting the gas from the cylinder to the probe tip, and in this case, through additional mass flow controllers as well. So analyte spiking doesn't seem to be the solution. It's a little bit better, it's slightly faster, it's a slightly more reliable result, but it doesn't seem to be the final solution. Just for consideration as well, this year we've had a new British standard published, 16429. Now, this one is actually relevant for the measurement of HCl by infrared techniques, which could potentially include an FTIR, but it looks at lots of other techniques as well. The interesting thing is that in that standard, it actually specifies that the test gas that's used to validate the analyzer on site has to be wet. And there's lots of data in the back of this. There's an entire annex in the back of this standard devoted as to why the validation gas used should be wet. And they've stated in there that the response times are much faster. And certainly that's what we've seen. Going back to the earlier slide, we've seen lab-based response times using a vapor generator down in the sort of 3 or 4 minutes, with cylinders taking well over an hour on some occasions. So certainly significantly faster response times. The other advantage of a hot wet vapor generator is the use of certified solutions. Currently, you can't get an ISO 17025 traceable cylinder of HCl dry gas, but you can buy a certified solution of HCl if you can vaporize that and get it into the system. And 16429 also states that wet gases are far more repeatable. So they're saying that the final result seems to be more repeatable by using a vapor generator. So in summary, there are lots of things that can cause differences when trying to perform sampling for HCl. So taking a close look at things like the materials that are used in the sample system, making sure there are no cold spots does seem to be very, very key. Making sure that if there's any parts of the system that are unheated, that they are lagged and kept as warm as possible, and that any unions and junctions are kept as short as possible. Old regulators, if you're doing your qual 3 checks on the SEM system on site and they're getting slower and slower over time, it might just be a simple case of getting a new regulator. If it's a test house performing validation checks on their system, then old regulators can be an issue. Ambient temperature, possibly. Not so much of an effect, but does seem to slow down some validations. And then the influence of ammonia is certainly a big one. For any site that's using ammonia injection or urea injection to control NOx, the possibility of the formation of salts for ammonium chloride is quite high. If you're expecting or if you're seeing any kind of ammonia slip and you're seeing concentrations of ammonia in the stack, this can have a large influence. One of the validation tests that we did many years ago was actually to do some dust testing on a site where we were struggling to get agreement between the two to look at the effects of these ammonium chloride salts. And we did 18 separate particulate runs, relatively high results on those, higher than the continuous monitor we're seeing in the stack for particulate. So the filters were sent away for analysis for chlorides. And we were seeing about 95% of the mass on the filter was chlorides, which was suggesting that we're seeing ammonia chloride salts collected on the filter, which is why so many of the test runs being done, we're seeing much higher concentrations of particulate, and it appeared to be caused by the ammonia and HCl reacting within the stack to form these solid salts. So having a good think about stack temperatures, sample temperatures, and matching systems to get the same result, it can be really key on these sites. And don't forget also, that isn't just an influence on a test house where we're seeing different results. You can also have this effect where you get a buildup of salts on a SEM system. So the SEM system filter in the stack is stopping these salts, but then as the stack warms those salts up, or as the sample system warms those salts up, they could be releasing HCl and ammonia, giving you readings on your SEM systems for HCl and ammonia, which technically aren't in the stack. They're coming from salts that have built up on the filter over time. So one thing we often say to clients now, if at all possible, before a calibration test is done for HCl, is to make sure those filters are cleaned or replaced before that test is done. And as you can see, it can be very difficult to validate an analyzer just to prove that it can deliver a valid result. It's not really just down to the analyzer. Generally, the analyzers are pretty reliable at reporting a result for HCl, but finding a sample system that can transport that HCl into the analyzer reliably and being able to prove that it's done that is quite a challenge in itself. So there's a slide there at the end just to sort of highlight some of the things that people can look at. So there's some common actions for test houses, things that they can be looking at doing, best practice for making sure they get the best possible result, and some actions there for the operator or the SEM supplier for them to consider, particularly before a qual 2 is carried out, to see whether or not we can try and get the best possible agreement between these two systems. So what needs to happen next? What's happening at the moment is the SDA have set up a subgroup looking at HCl management, and the plan there is to publish a best practice guidance document. So essentially everything that I've just whizzed through on that previous slide there, guidance for test houses, guidance for site operators and SEM suppliers, and I believe that's hoping to be coming out in the next month or so. So that there'll be a guidance document that people can refer to try and find the best way to get a result. Fundamentally, there are, as you can see from this presentation, there are a lot of questions raised. Really, we'd like to see more research, more trial work done to see how much each of these effects are causing issues. And I've seen in some of the presentations earlier this morning that as ELVs are coming down, this challenge is going to get more serious. So trying to prove that everything works down at these low concentrations is going to be a real challenge over time. Unfortunately, there isn't a lot of funding available, and any testing that occurs at the moment is fairly ad hoc and is down to sort of individual test houses as and when we find the time to see what we can do to improve. And the final thing is development of new equipment or techniques, so anything that comes along that may speed things along. And I'm quite glad to say at the moment that Socotec are currently validating a completely portable HCl vapor generation system. So we're hoping to be able to move away from dry gas validations and start doing our validations in line with this new European standard where we can produce HCl vapors on site. Yes, watch this space.
Thanks very much indeed, Andy. Despite your fears, we have actually overrun a bit.
Sorry, my stopwatch stopped halfway through that, so sorry about that.
There is a question from Mark Coleman on the system. Thanks, Andy. In theory, the sampling system of a type-approved PAMS should not be changed. Of course, in reality, it is often necessary. In the past, an MCerts for type approval of sampling systems has been mentioned, so specifically approval for the sampling system. Do you have any views on that? Good, bad idea?
Yeah, I think it would be a great idea. I mean, one of the things that we would like to move away from, because of this uncertainty of dry gas cylinders and whether they can be validated, we would prefer to see our sample systems that we use on site validated in the lab against a vapor generator. But at the moment, as I said, those vapor generators tend to be lab-based bits of kit. So it would be great to have those validated. And if there was then a system for certifying sample systems to prove that a particular configuration, particular material can transport HCl to an analyzer, that would be ideal.
And I just had one quick question. You talked about solutions. Are they stable over long periods of time if you use a solution in an evaporator?
Yes, I think so. The solutions that we've got that we're testing at the moment have an expiry date of sort of 2 years on them. To be honest, the reason we're looking into this at the moment is over cost. HCl cylinders can be prohibitively expensive, and we're using a lot of gas to carry out a validation. A 1 litre traceable solution of HCl is £10. If it goes out of date, there's no issues buying a new one.
Yeah. Are you confident it's actually delivering the correct concentration in the vapor phase?
So yeah, what we're doing is trying to vaporize a known concentration and then see that result come back on the analyzer. I mean, this technique has been around for a while. I know a lot of the SEM suppliers have got equipment that use vaporizers, but it's coming up with a system that was well, validating a system that is portable enough that a test house can simply turn it on site and get a repeatable result. And those tests are underway as we speak. So I'm confident that we'll come up with a site-based solution that provides a faster, more reliable result. So fingers crossed.
Great. And just one comment. I know that the emission limits in the States for HCl from some processes are very low indeed, and a lot of work has gone into measurement at, I think, 3 ppm sort of level. So, and obviously the actual emissions will be low. So there may be read across from stuff that's been done over there that you could get hold of to inform what we do in Europe.
I think the measurement of HCl, I think I've said earlier, the measurement of HCl by the analyzers is quite robust and reliable. They're pretty good at systems. Our issue is validating sample systems. So that's the area we want to be concentrating on next.
Yeah. Thank you very much indeed.